All right, gang, Math 5500. Sorry for the abrupt ending. I don't know if anyone noticed what I did, but what I did in the before is completely embarrassing. I saw it, so I just stopped the video and trimmed it out a little bit. What I did was that when I created my sum of squares there, I got sloppy. You can go back and look at the end of the video to see how sloppy I got. Instead of creating the error, I created the sum of squares error from the predicted y, which is that's just wrong. So anyway, that's been corrected. So I actually do have the correct sum of squares error and the correct mean square error. Notice the mean square error is the sum of squares is just, the mean square error is found by taking the sum of squares error divided by n minus k, number of predictors minus 1. So minus sum of squares error divided by 17. All right, what I want to do now is I want to calculate D3 that we talked about previously for and so I tell you what, I want to regroup here. Let's go over to d sub I, and we see that d sub I, is found, by these parts. So let's just find those. So I need the error for the third case. So that looks like it's negative 3.176. Then I have the number of predictors, which is 2, plus 1 is 3. And the mean square error is 6.468. Now, the diagonal element, we want the third diagonal element. So if I go to HII, we get 0.372. And of course, down here, we get 1 minus 0.372 quantity squared. All right, so let's find that. So looks like D3 is going to be so obviously I can just use 3.176 divided by the quantity of 3 times 6.468. And I need to multiply that by 0.372 divided by the quantity, 1 minus 0.372 squared. So D3 is 0.49. Interesting. Okay. So what we have now is 0.49, right? I got something different earlier, but I rounded everything to the hundredths instead of thousands. So I'm sure it's only off by like 200. So what we need now is we need to dive into the F distribution, and we want to look at 0.49. And we want to get the percentile ranking. So it's going to be super easy. So remember that the degrees of freedom for this is k plus 1. So we have 3 predictors. And then we have n minus 2 predictors minus 1. So the percentage below D3 is, let's just call it 31%. So when we go to our table previously, we see that 31%, 0.31 resides in this interval. So we have a moderate influence for the third case. So nothing that should bring any concern to the third case. And again, I didn't know if there's any concern or not. I just chose the third case because I just did. All right, there was no reason. Now, I want to show you some things that you can do in R that are kind of cool. If first of all, I have to create my model. So I have body fat predicted by triceps plus thigh and summary model. So we get our estimates, and again, only thigh is statistically significant in terms of predicting. If I want to pull out my ANOVA, and you'll see that our mean square error is 6.47, which we better have gotten before. It'd be kind of goofy if we didn't, so 6.47. Now, something kind of cool is we have some things that we can look at. Now, the first thing is we have a command called influence measures, and it actually gives us more than just influence statistics. And I'll run through a few of those. All right, so let's take a look at that. Now, what this does is it gives us some DF betas and DF fits and some covariance stuff, some variance inflation factor. The only thing that we've really talked about in this class so far is the last two. And what we have is we have a Cook's distance. Actually, for the third, this would be 0.49, which is really what I got before. So I may have made a typo. We got 0.52, but I'll tell you what I did before. I didn't round off. I didn't round these off. I actually used the values, so that's why I got 0.49 before. So in the hat column just gives you the H sub I. So we'll just choose one at random down here. This H1515 is going to be 0.3332, which we have up here someplace. What did I say? Well, let's look at the last one, 0.0501. 0.0501. Okay, so anyway, they match up. So what's kind of cool about this is it gives you a column with an asterisk. And if there's an asterisk, it means that one of these measures is actually of concern. So something for the third case is of concern, something for the fifth case is of concern, and something of the 15th case is concerned. Now, the cool thing about it is I can do summary influence measures for the model, and I can actually focus in on just those three. So it doesn't give me a generally speaking concern, it gives me a concern specific to the measures. So you'll notice that none of the Cook's distances or none of the half values on the diagonal turn out to be a concern, but there's an issue right here with some covariance stuff. There's some issues here with some DF betas and DF fits. Again, we're not going to study that in this class because I need to end lesson 7 sometime in the near future. But we will go into all that in 6500 if you decide to stick around. Another kind of cool thing that we should take a look at, and we have to install a package first. And I've already installed it, so all I have to do is just access it. And it's called LM test. So there's something called DW test, and I can run this after running my model. And let me tell you what this is. This is the Durbin-Watson test, And this gives us an indication of if autocorrelation is an issue with our residuals. Now, what's autocorrelation? First time I've talked about it in this class. Think of autocorrelation as just a degree of or magnitude of a correlation that's focused on the residuals. And if it's kind of hard to say how. Okay, let's just say that if a relationship is incorrectly specified or incorrectly modeled. In other words, if we've used a linear model when a linear model wasn't appropriate, then the residuals could be correlated. Remember, we don't want that. Our errors are supposed to be what? They're supposed to be random, shotgun blasts, no discernible patterns, certainly not correlated. Well, for the Durbin-Watson test, this tests the assumption that our residuals aren't correlated. So if we get a p-value greater than 0.05, then we can assume that autocorrelation is not a concern. If we get a p-value less than 0.05, then it turns out that it is a concern. So that's what goes on there. So it's just a way to address autocorrelation of our residuals. Typically, autocorrelation, at least this way I think about it, typically deals with time series, but it is a kind of a clever way of using Durbin-Watson to address something specific to linear regression. Well, I'm done. I can't think of anything else that I really want to throw at you. I guess you could say this concludes Math 5500. Congratulations. Take care.